Okay, let's clear up the confusion around the low, medium, and extra high thinking effort levels in the Qwen 3.8 27B model. We'll also discuss the difference between these effort settings and the newly introduced reasoning budget. To clear the confusion around these reasoning efforts in Qwen 3.8, I will try to explain how pre and post training work in modern LLMs in simple English. Once you understand this, 90% of things will get clear automatically. By the way, along with the training part, I gotta explain the Jinja template part as well. Though it's not that complicated, its role in Qwen 3.8 is extremely vital. Let's begin. So the first phase of building an AI is called pre-training. Basically, this is essentially like locking a student in a massive library and making them read, I don't know, years and years of math, textbooks, science journals, encyclopedias, history books, just everything. Okay. And yeah, don't forget to destroy those copies. So in the pre-training phase, AI is just absorbing massive amounts of raw general knowledge. They learn the structure of language, they memorize historical dates and formulas. But at the end of pre-training, you basically just have a base model. And that base model is, practically speaking, kind of useless for direct tasks. I mean, that student in the library might have memorized every formula in calculus. But if you sit them down and hand them a complex, multi-step word problem, they might behave a bit awkwardly. They might just start quoting the textbook at you instead of actually calculating the answer, because they haven't been optimized to be a focused problem solver yet. They have the knowledge, but not the application. Which brings us to the next phase, which the industry calls post-training. Okay, so post-training is just the umbrella term for everything that happens after that massive foundational pre-training phase. Sticking with the student analogy, post-training is when you pull them out of the library, sit them at a desk, and say, okay, you have the knowledge. Now you're going to become an excellent problem solver. Here are 1,000 difficult math problems. Solve them, and I will tell you if you are correct. That's where RLVR comes in. It is short for reinforcement learning with verifiable rewards. RLVR is one of the key ideas behind the recent jump in reasoning models, and the intuitive version is actually much simpler than the terminology makes it sound. The core idea is, instead of teaching the model what the correct reasoning looks like, give it problems where you can automatically check whether its final answer is correct and reward it when it succeeds. Imagine the model generates thousands of attempts. Something like this. Here is a problem. Attempt 1 wrong, attempt 2 wrong, attempt 3 correct, attempt 4 wrong, attempt 5 correct, attempt 6 wrong. The training algorithm says, whatever you did in attempts 3 and 5, do more of that. And whatever led to the failures, do less of that. So instead of imitating a human solution, the model is gradually learning a policy for finding solutions. It's like teaching a child how to play chess. You give the child a chessboard and explain the rules of the game. After thousands of millions of games, they eventually develop strategies that nobody explicitly taught them. In RLVR, the most important factor is verifiable. That's where the current AI race is heading. The quality of the verifier is absolutely critical. In RLVR, there is a problem called reward hacking. Instead of learning, models tend to maximize the reward by using shortcuts. Verifiers are accurate in mathematics, programming, formal proofs, or grammatical mistakes. But how do you verify a creative work? So the competitive advantage isn't simply who has the biggest GPU or TPU cluster. It increasingly becomes who can build the best training environments, verifiers, synthetic problems, reward functions, and RL pipelines. This is one of the reasons why Google's Gemini model is still trying to catch up despite having massive compute power and raw data. Anyway, coming to our Qwen 3.8 27B, let's compare this with GPT-OSS and how they trained their models, or more precisely, what kind of reward signal they used. OpenAI explicitly trained what they call variable effort reasoning directly into the model's internal policy. It means they literally trained the model during that RLVR phase to support three distinct separate reasoning gears: low, medium, and high. So essentially, it's baked into their model weights. So in AIME 2024 benchmark, which is a brutally difficult math test, the GPT-OSS 20B model scores 42.1% on the low reasoning setting. But when you switch it to medium, it jumps to 80.0%, and on high, it hits an incredible 92.1%. I mean, it's literally acting like three different models. So when it sees the reasoning is low, it knows from its training to aim for a quick conclusion and admit its final answer early. But when it sees reasoning high, it natively expands its search tree. It runs self-reflection loops. It digs deeper. It challenges its own assumptions. The model actually changes its internal persona. But here is a big but. There is no equivalent primary documentation showing Qwen 3.827b was explicitly trained on low, medium, or high effort conditioned policies. It doesn't have gears at all. Instead, it was trained on a unified binary system. It either thinks or it doesn't. That's it. So they basically taught it that when the think tag is activated, just keep reasoning until you organically feel you have solved the problem. It does not have a medium or low or extra high intelligence setting natively baked into its weights. This is an extremely important point, and that's why I said you need to understand how Qwen models are trained. Their verifiable reward is basically getting the right answer. It doesn't matter how many tokens it consumes. Now, the next question is, if Qwen is trained with just binary signals, that is, think or no think tag, then how on earth Qwen team implement various reasoning efforts? They certainly didn't train their model like GPT-OSS. Well, the low, medium, and X high effort levels work through prompt level steering directives injected directly by the Jinja chat template before the prompt hits the sampler. Now let's understand what a Jinja template is. This is the last puzzle. Basically, a Jinja template is the recipe for constructing the entire prompt that gets sent to the model. And it is different from the system prompt, mind you. Think of it this way. You give an LLM an abstract conversation. The system prompt is something like, "You are a helpful assistant." Then the user prompt is something like, "What is 2 plus 2?" But the model doesn't receive a system object and a user object. Eventually, everything has to become one sequence of tokens. The model might expect system tag, then your system prompt, end tag, user message. For this example, what is 2 plus 2? End tag, assistant tag. The Jinja template is the program that constructs that sequence. And LLMs need that format because they are trained on this specific format. So imagine you mess around with some Jinja template tag, and the model like Qwen 3.8 is trained on a different sequence format. The model may still work, but you're no longer reproducing the format it was trained to expect. Modern AI models often use pretty complex structures. That's exactly why Jinja templates are usually the first thing to check when a model starts acting up. When you load Qwen 3.8 27B into tools like LM Studio, Olama, or llama.cpp server, it automatically comes with its own Jinja template, so you usually don't need to tweak anything. But if it does act broken, you can just manually upload the correct one. I've linked the highly recommended Jinja template in the description below. It's just a tiny text file. Go ahead and download it. In LM Studio or Unsloth Desktop, you can import it using their import button. If you're using a llama.cpp server, use the chat template file flag followed by the full path to your Jinja template file. Okay, coming back to our original question, how Qwen implemented reasoning effort even though the model is trained with thinking on and off tags. So, like I was saying, when you toggle reasoning effort, the Jinja template dynamically inserts tailored behavioral guidelines into the system or context block to constrain how the model approaches the think phase. On a low thinking setting, the Jinja template injects constraints directing the model to resolve only the immediate unresolved decision, avoid exhaustive multi-step planning, and close the think block quickly once a direct strategy is found. On a medium level, the Jinja template limits the model's open-ended exploration. It directs the model to focus reasoning strictly on the current turn, check key assumptions, and move to generation without drafting redundant intermediate summaries. And on the X high or extra high setting, Qwen behaves with zero prompt constraints. The model explores edge cases, drafts intermediate tool calls, verifies proofs recursively, and only closes the think tag when it reaches high internal confidence. And this natural language prompt works without touching the model weights because Qwen has strong instruction following capabilities in its system prompt. And as I promised at the start of the video, this is actually very good news because this is not trained like GPT-OSS, where low thinking means you are not using a less smart model internally. Technically speaking, the base parametric intelligence, or the weights of Qwen 3.8 27B, never changes whether you set effort to low, medium, or X high. That's good news. You are guaranteed to get the same model weights. Only the number of steps will be different. But don't go overboard. Keep in mind that use low thinking only for very simple tasks that only require one or two logical hops, for example, summarizing an article or explaining a concept, standard API wiring, or straightforward math. But never use low reasoning effort for seemingly complex tasks, because low thinking mode can make the model deliver a dumber answer if the problem demands multi-step verification. If you use low mode for correct tasks, you will produce answers of identical quality to X high with fewer tokens and less time. Now, let's clear up the confusion between effort level and reasoning budget. First things first, they are entirely two different things. Effort levels like low, medium, or X high are set by the Qwen team. They use the Jinja template, which we talked about earlier, to guide the model's behavior. On the flip side, the reasoning budget is a hardware-level safety net managed by tools like Llama CPP or VLLM. Think of it as a limit on how long the model can think before it's forced to stop. For instance, if you set the thinking effort to medium, you might want to cap your reasoning budget at 4,000 tokens just to prevent the model from rambling on forever. The Llama CPP team implemented this budget because Qwen 3.8 can sometimes get a bit obsessive, struggling to gauge task complexity. Since it doesn't natively distinguish between simple and complex tasks, its RLVR training, which rewarded correct answers regardless of token count, led to some reward hacking. It learned that more tokens often meant a better answer. For example, when I asked for a simple Excel shortcut to drag a formula, it spent 4,000 freaking tokens debating whether to use Control plus D versus copy pasting several times, even though Control plus D was the correct answer right away. It's not like the Llama CPP team deliberately wants to complicate things, right? I mean, they literally had to add this flag to curb that overthinking. Oh, and just be careful not to set the budget too strict either. Think of the reasoning budget like a bouncer. If you set a strict token limit, let's say 2,000 tokens for a complex task, the model might be mid-thought on a crucial step when it hits that cap. The bouncer then grabs the model and forces it to output a final answer immediately, ready or not. That's why you shouldn't use the reasoning budget as a substitute for reasoning effort. You're not changing the model's strategy. You're just cutting it off mid-thought. There are some PRs in Llama CPP to nudge the model towards a smoother cutoff instead of yanking the cord abruptly. So if you are going to remember only one thing from this video, then remember that lowering the thinking effort setting doesn't mean Qwen loses any smarts. That knowledge doesn't just vanish. Even if you drop from extra high to medium effort, the model's internal weights and its ability to handle tough problems stay exactly the same. It doesn't turn into a less intelligent version of itself. It's still just as sharp. With that said, let's wrap up here. Thanks for watching, and I'll catch you next time.